Pin just in case. But there's only one person, so I can't pin speaker. Okay, if you notice that someone joined, then just let me know and I'll try to.
Or I'll join, you can initiate that. So
No, it's fine. It's just when there's only one person, I can't really pin the.
Yeah, so he can be the second.
Okay, yeah, you can.
Because in one talk it's Ahmed along with the board.
Yeah.
In the recording.
Yeah, that happens more times, unfortunately.
In the recording, so what's and yes.
Okay, thanks. Yeah.
it's kind of yellow. Yeah, lines are there.
Be good. Okay, yeah. Hello, welcome everyone. Today we will have Aviral talking about KMOC. What is its master's project? Okay, yeah, that's perfect done. So please feel free to start.
First of all, thank you everyone for coming here. So I'm presenting you my master's work that I did with Professor Aviral. This is based on KMOC formalism developed by Kosovo and company. And this is basically an Indian state formalism that is used to derive classical observables using Feynman amplitudes. And so the kind of classical observables that we are talking about here is a momentum impulse in a scattering process on two of the particles, or angular momentum impulse, or momentum radiated in a two scattering particles. So, like I said, we are looking at two scattering. And since this is an Indian state formalism, the only information that we know about the particles is about the in states of them. We don't know anything about the out states. And for simplicity, we'll just consider the particles to be massive, which are scattering off each other. And so we assume the particles wave function to be something like that, where phi p1 and phi p2 are the wave function of the particles. They will have to behave in a certain way so that we have a so that we can look at a classical limit. And we know what p1 and p2 are. These are just this is just the tensor product of two particles that are incoming, and they are in the, since they are scattering of an impact parameter. This is the pattern. So what we know is this is the in particle, the incoming state of the particle, and we know that the outgoing state of the particle would be.
So okay, what does the integrals mean?
Okay, this is integration over integration of the Lorentz measure. Here we'll only look at the positive solution, and we know that the out state of the particle would be the S-matrix times the in state. So this is where the Feynman amplitudes will come into the picture.
So it's on shell. The
Yes.
incoming.
These are the incoming particles, so they are on shell.
Yeah.
Yes. So, say we are trying to look at some particular observable and trying to calculate what the classical value would be. So, we know that here we can break down S using 1 plus sine t, where t is the transfer matrix here. And we know that, say we are looking at a momentum. So P1 mu operator acting on the in state will give me the value P1 right? Now, we know what, since we are trying to calculate the momentum impulse, we need this quantity which is P out minus P in.
P1 out. Oh,
Yes,
yeah,
P1. P1.
Yep.
Sorry. And now P out, we can write using this equation, and you can just write this P operator acting on S-matrix times. And yeah, so once you put in the transfer matrix, this identity, this equation, and use the unitarity property of S matrices, you will arrive at this equation. But I'm writing this for any general observable. Here, this sign is a sign in. Like to observe that this both are signs here, because like I said, this is an in-state formalism. Plus right. So we see that we have the value of the observable, the expectation value of the change in the observable written as sum of two parts. Now here it is clear that Feynman diagrams will the Feynman diagram will come from the fact that we have terms like this, right? So I'll just give you a brief example of scalar QED.
So let's see. Oh, why does O have an index on it in the expectation?
O would be like P, right?
Yeah, but it doesn't have to be.
It doesn't have to be.
So the index doesn't have to. It looks very confusing if you have an index on the O on the left, but no index. And so are you doing the expectation? What is the state you're putting that out? The in state on
Yes.
both sides.
Yes.
Now, how do you get where does the scattering, on the left hand side, what is the state?
It's this state.
On the left hand side?
Yes.
So where does the T come from?
T comes from dividing the S-matrix into one plus I.
So where does the S matrix come from if you only have in states?
Yeah, could you explain the in formalism once? So like,
In
how do you get into an
in formalism in this sense is just that we have just the in state of the particle. We don't know what the out state is.
Right, but the T tells you something about the out state.
Yes.
So where did the T come from on the right hand side there?
Like T here as of now is just a
No, I understand there, but in the formula for the expectation value of delta O, where does the T come from?
T comes from the fact that in this thing you put S equals to 1 plus I.
Oh, that's how you defined. Okay, I see. So you do have in the left hand side, the T comes from the delta O.
Yeah.
So you're sort of evolving the operators, not the states.
Yes.
and the commutator?
Sorry.
And the commutator?
Commutator comes from the fact that we are using the unitarity property of S plus X. That is one. That's So I have to look it up, but it comes from the unitarity property of S matrices. So when you translate, it translates to something like this. Yeah. Maybe not exactly this, but yes. Yeah. So our next step is to just put in this initial wave function. Now, what's your question?
Yeah, I will get that.
Uh, So we just have to put in the initial wave function in this equation, and we'll have an expression for this thing that I will call as I1, the kernel. This is the. Right. So just to show you the form. It's
Yeah, I guess I'm still a bit confused.
yes,
So in your formula for delta P,
yes,
it's defined as operator P out minus operator P in.
the expectation value.
Sorry?
So this is just a value, right?
Yeah, but right,
So
but the P out is then defined in terms of the operator acting on some states.
yes,
So how do you get, I can,
this is the.
P is an operator, but the way you defined it, it's a state. So how do I get an operator back?
Like, P acting on the instate gives me the value
Right,
of this, right?
right.
So okay, I'll just clear out this.
Yeah, I think like his P out definition is this.
Yeah.
P out itself is not an
I'll-
operator. P out is me acting on S acting on him.
Okay,
Yeah,
but
but
then
then-
why is then a hex on P out?
Yeah,
Yeah.
yeah.
Maybe it's just valid.
Ah. Okay, now it starts making sense.
Yeah.
Yeah.
Is it right? This is for the out particle, this thing, and this is the thing in momentum.
Right, so this is, so the delta P is expectation value of P in the out states
Yes.
minus expectation value of the P.
Yes,
in the-
yes. So basically what we are doing is we are having two particles that are scattering off each other and then going off far off. So we want to calculate what's the initial momentum of the particle and the final momentum, and then we need the impulse for one of the particles. This can be done for the second particle as well, but we are doing it for the first one only. Yeah, and so this, once you put in your initial wave function in these equations, you have for I1, this is the expression. What amplitude I have written there is because, like I said, you have this T sandwich between two incoming instates of the particles.
Wait,
Yeah.
wait. So now you're writing a formula for the first
That's yes,
thing,
that's it.
and you're writing the in states. Okay, but then we have some Q4 integral, where does
Yes.
that come from?
So yes, yes. So Q here is P1 prime minus P. So P1 prime is the momentum of the K, and this is the momentum of it. Right. This
Okay.
Q is here, Q here is not the momentum transfer. It might seem like, so I was just converting it into a diagram, you will be like, here these two particles coming in, momentum P1 and P2, and going out with the momentum. P1 plus Q, and P2 plus P2 minus Q. It might seem like these are two particles, but since it's a Feynman diagram, Q, like I said, since this is an in state formalism, P1 and P1 plus Q are both the in states of the particles. And Q is not the momentum transfer between first and second particle. This is just the in state.
But it's still, okay, a little bit strange to me. It's not like you're fixing the momentum of the incoming particles. You take all momenta, which are all mass shell,
Yes.
essentially, because you have the delta function there. It doesn't fix it completely, but you give some.
The initial P1 and P2 are fixed.
Or no, I don't understand it even. You have a delta 4. Is it really a 4-dimensional delta function?
This one?
Yeah.
Or
Or
this.
how
No,
much?
this is just delta function, I think.
No, yeah,
Yeah.
yeah, okay, that makes sense. So you're sort of, you're fixing that p squared is equal to m squared, but you still have all directions of p available to you. So you're in your in state, it can be, the piece can be in any direction.
Yes. I'm not sure about that interpretation, but I generally just think of it as like that you have these, maybe when I'm doing the classical interpretation, these two are incoming, stacking over the impact value terms going on. And so integration here is mostly what, like in practice, what we will do is integrate over the Q, the momentum transfer, the momentum mismatch.
Right, the Q came out because you took, actually, in somehow, somewhere, you got the bra with the cat and you got some delta functions. So
Yes.
in principle, you would have 4 different momentum integrals, but one dropped out because of some kind of
Momentum conservation, right?
Sorry,
You will remove one P from momentum conservation, right?
one P,
Like
which one?
instead of P1, P2, P3, P4, you introduce Q and remove one, but like.
Like I said, this is not P3, P4. This is not the outgoing particle.
Yeah, okay, but,
This is the incoming particle.
okay.
Yeah. It's not good. I didn't get it.
Yeah, no, I guess it's the same thing, right? So I agree with the statement. So you have in your in state, there are 2 momentum
Yes.
values in the in state which are integrating over.
Right.
And in the in ket,
Right.
sorry, in the
You have two
in bra there are 2 more.
Yes,
But here there are only 3 momentum functions, so you somehow got rid of one.
exactly. Yes. Yeah, that's because of the momentum.
Sure. And how did that telephone two P1 Q come from?
Yes, this came from the fact that even this thing has to be on shell. So delta of P1 plus Q whole square minus M square. You put this, that's this thing, because P square equals to M square.
Right.
Right? Yeah. It's clear. Yeah, and we have another messy equation for I2, but diagrammatically it would just look like, again, these P1, P2 particles coming in. And yeah, diagrammatically, I2 would look something like this. We need to evaluate these kind of diagrams. Here, these are the intermediate states. These intermediate states came from the fact that we are putting in an identity here. So we need to sum over all the intermediate states possible. Again, P1, P2, same. P1 plus Q and P2 minus Q are the out states in this Feynman diagram. but this is not the actual picture. So, yeah, and
So here they are the out states.
no,
They're still in the in states.
yes, these are in states.
Okay.
Yes, this is just some number, and we interpret it as a cut in a fragment line. The way the expressions are, I'm not writing the expression because it's will take the whole space left. And yeah, okay. Also, these will be on shell. So, yeah, but how do we come from this to the classical value is a series of steps that they mentioned. They have their own reasoning because you need to look at so the basic idea is that we want our files here to behave in a certain way so that we get a classical calculation. So we want our particles to have, since they are scattering over an impact parameter, and they have their intrinsic distribution among themselves, which is
Okay, so but these are the wave functions in configuration space. These are not the files because they are in momentum space.
yes.
So it's a Fourier
This
transform.
is spread in the position space, and this is the separation of. And we want these particles to be not too much spread apart, so that
Right.
otherwise the quantum effects will come into the picture.
So this is some kind of Gaussian.
It could be any function, but it's generally they have given examples of Gaussian function because it's.
But then you the Fourier transform and the
Yeah.
original are the same form. So it makes
Right.
more sense, I guess.
Right.
But
It's easier to interpret.
and you took out the impact parameter and put it in the exponential there, no? The e to the yeah.
It's right. It's here.
Right. So you don't really need to put them in different places. That's already taken care of with this
Yes.
impact with this e to the
Right.
b.
Right. So like, this is what we want from our wave function, but how we achieve it in terms of this is by rescaling different parameters here with the powers of h. And I'll just give you a series of steps because the whole argument they are giving is a whole series.
Oh, I see. Okay. That's why you cannot fix the momentum. You want it to be on shelf, but you want to be able to change it a little bit so that you can make a wave function which is more localized in configuration space. That's why it should.
Right. Exactly. So yeah. So the pedagogical step that they are saying, I'll just mention you the steps, is that in these kinds of expressions that we will have, we have to scale our momentum transfer here. We have to scale all the inner particles, the summed over particles. We need to scale if there is any radiation emitted, and then of course we have to scale the coupling constant P. Or whatever it is, G with the appropriate power of H. For E, it is this. You scale it with 1 over root H. And then you effectively look at the lowest power of H in the expression, and that is claimed to be the classical value. So I'll just do one calculation here. So let's maybe look at scalar QED, and scalar QED has, we know what the Lagrangian looks like. Then you have these two particles.
You can move the other board of one.
Yes. This is for particle one. So you have these two particles, they're Lagrangian, and you have your field. So putting in, I'll write a similar expression to I1 only, and it would be Q. So this is the expression that we get, and this is claimed to be classical impulse of classical momentum impulse for this kind of scattering where you have two particles.
So what do you have there? Q A dot?
Yeah,
What is
A here will be the amplitude of the
and Y dot?
Because it, like I wrote dot because in my notation A is the amplitude and A dot is the amplitude with the scaling done. You take out the powers of H in Q.
Normalize.
Okay.
Yeah. Sorry.
Normalize.
Not normalized.
Yeah, what I mean, right? The scaling.
Scalings in H, yes, for the propagator Q. So A we know those. So since we need to scale Q, we have then this will get the so yeah, solving this kind of integral,
Right. And the Q is the operator.
Q is the operator.
Comes from that.
Yes. Yes. Q1. And once you solve this integral, and it will give you the correct momentum difference. This is what.
So the A, okay, I can see the propagator, 1 over Q squared. That's the propagator, right?
Right.
And the stuff up comes from the vertices.
Yes, exactly.
So you
The
do.
normal Feynman rules for this kind of Lagrange.
What?
It would okay, so if I use this P1 plus P dash.
Oh, okay, yeah. Okay.
This is P1 dash, this is P1 dash.
Right, so there's one is the derivative, you get one P, and then there's an H and a I. Okay.
And your scalars are massive, I guess. You wrote
Yes.
some masses here.
Yes.
Okay, but you didn't write a mass.
Mhm. Mhm.
Yeah. Is that right? So yeah, and this result is exactly what you get from classical calculations.
So don't you need to include some other diagrams or you just
Yes.
you think, I mean, is it obvious that this is the one?
Yes, I'll tell you. So this expression, like I said, I have written because I am calculating I1. And I1 is, if you analyze, is that I1 is at a lower order than I2. Because I2 has these two transfer matrices right there. So if you are trying to look at a higher order scattering, then we need to consider the box diagrams, triangle diagrams, and everything like that. But since we are working in order E square, then we only need to consider the pre-level diagram. for this kind of scatter. But this exercise can be done for higher orders, and for E4, we need to look at all the possible diagram. Add them up, and I2, then you also need this I2 contribution, the cut standard diagrams, and this will be useful, but again, the calculation is much more difficult.
Do you get also
Yes.
loop in momenta that you have to integrate over?
Yes,
So you get divergences?
yes.
So can you generally say I was a tree level and I2 is one loop?
I1 is,
Tree level and I2 is one loop. Can
No.
you make such a?
no. I1 is one loop, it's true. I1 can also be one loop, but I2 are the cut diagrams. I'll draw an I2 diagram. I2 would be something like this. Like two trees joined together. This would be
Why do we have a commutator in I2?
commutator in here,
In I2?
for the same reason as it's in I1, because
I want, that's clear because you have A's on both sides.
Okay, I can derive it for you, like, but it's like, like I said, it comes from the unitarity of transform process. It's like very trivial once you do it. And also one can do this calculation for particle 2 as well and check that delta P1 plus delta P2 is 0, which is what it should be, the basically angular momentum conservation. Yeah. So this is what was given in the literature and everything till now. So we tried doing the same kind of calculations for angular momentum impulse. And by finding the angular momentum to be mu wedge x nu, and wedge means just the antisymmetric product as well, and putting in this operator in that equation and solving everything. I'm not doing the calculations now, but what we will get is just again looking at the lowest order, that is the tree diagram. So this is what we get as a angular momentum impulse for the same kind of situation. And here we see there it is logarithmically divergent. And
Why do you have two different masses?
we can assume that two particles have two different masses as well.
So, but then you need some.
Something, yeah. Could be same, it could be different, because the scattering that we are looking at is electromagnetic scattering because of the charges. So masses don't really play that much role in at least the force. It doesn't depend on force scattering. And to have a better idea of what this is, say we are looking at let's go to a particular reference frame where we choose our medium to be energy 0, 0, and some right, we can do this, and once you put in your values, your J in your values, you see that Jij is 0, but delta Ji0 is not equal to 0. It is some infinite quantity. It's a logarithmically divergent quantity. So this is kind of problematic because once you do some Lorentz boosting, you will see this non-conservation of angular momentum in the zeroth component transferring to your three angular momentum as well, which means our angular momentum is not conserved in two particle scattering, and but it should be like that. So this is the question that we were trying to look upon, and this everything can be understood classically as well. And I'll just give you a brief picture of what the classical.
Yeah. What is the classical interpretation of Ji0?
Yes. Ji0 is, it's called as mass moment in the literature, and it's like energy times the position minus t times the momentum. That's the part. Yeah, and so we have these two particles. Just to be clear about the what kind of scattering is going on. We have these two particles coming in from infinity. They are scattering over an impact parameter bu, and you have this slight deviation in the particle trajectory, right? And depending on the order that we are looking at, we can iteratively calculate the trajectory of the particle. This could be at order e square, or this could be something at order e4, like that. And so we have no idea of what this result is and why this is happening. But fortunately, there was a paper by Sam Grala, the above one that I mentioned, and they basically try to calculate all of this quantity classically. The mass moment, the momentum, the angular momentum of particles as well as fields in this kind of setup. And what they came up with was exactly the same result. This logarithmic divergence, the logarithmic divergence of angular momentum, and the Ji comma zeroth component behaved something like this, which time. This is minus infinity, this is like infinite time. And this is, it shows that since our particles trajectory at minus infinity and infinity are logarithmically divergent, we are getting this this extra quantity. So it means that our initial, like what we have as an intuition is, at asymptotic times you have your particles behaving freely, or they are expressed as a plane wave, right? But this interpretation is what they said is wrong. That even at infinite times, you have these interactions in the between the two particles, even if they are infinitely separated, because our potential is known by R form, and this gives rise to this logarithmically divergent.
So if you give a mass to the photon, you wouldn't see this.
Yes, yes, exactly. That's fundamentally because our amplitudes are higher divergent, and one can see this by just looking at a soft photon emission. So that soft photon emission is basically when you can go, a particle can come in and emit a soft photon, and this photon can have Q going to 0. When this Q goes to 0, you have this higher divergent in any amplitude.
So did you try to put in the mass for the photons?
We did not try to put in the mass of the photon, but we tried something else. Putting a mass to the photon, I don't know how that would.
The simplest thing would be just you put the mass in the propagator, use quite constant stuff.
Yes, but would this, I don't know whether it would affect these kind of terms, the normal. Sorry, it will affect it. Yeah, it would. So, yeah, then that would also defeat the purpose of, maybe like it could be checked if the result is still interpretable. And so what we did is, so we knew that the problem is because of these long range interactions of two particles at asymptotic times. And what I maybe, yes.
Or maybe if you try to do it in higher dimensions, where the Coulomb interaction is zero, the decrease is much faster. Maybe that could be a different way of checking if
Yeah.
it's.
Yeah, I didn't think about that, but what we did was, yeah, that could also be done. What we did is we used Father-Pulish states. So Father-Pulish states is a formalism where you in a quantum field theory, generally it is assumed that potential goes to zero when you look at the asymptotic times, but they modified the usual definition of our scattering matrices with these are the molar operators, and this is defined like this. But what they did is, they said that this is not how we define molar operators because your asymptotic potential is not zero, and they define it in a new way. Or they just added a factor. They said we'll use an asymptotic state as a asymptotic Hamiltonian rather than the free Hamiltonian for the particles to evolve. And that effectively added up to your new S-matrix to be this is the traditional Lancelot matrix, and where U will be these two particles of these two terms. So basically, you dress your S matrix with these new states, and this is claimed, and this new S matrix is claimed to be IR free. It is IR finite, and so our thought was maybe this once you put in this S matrix instead of the usual S matrix, this would solve the problem of IR divergence, and it kind of did. And you can already see the same kind of factor emerging in our exponent that we had for the divergence there, this factor. And this factor indeed accounts for the long range interaction that we can see by taking stationary phase approximation for an incoming particle. That is we knew that our particle was something like dot q and v1 dot q2. Now, in the rest states, it would be right. And once you use stationary phasor approximation, you get the classical trajectory of the particle. And that trajectory of particle is exactly the logarithmic divergence of particle. And yeah, so in theory, we know that particle states or the IR free or IR finite S-matrix would account for would solve the problem of divergence in KMOC formalism. But to exactly implement it is a little difficult. We tried doing this and we got the correct IR finite result for order e to the power 4. We could not get this for order e to the power 2 is because there we are dealing with transfer matrices and Q in itself has a factor of 3. So when we are looking at order e square, we will need to take the part of s equals to 1 plus iota t. We need to take this one part, so the part with no interaction to have order e square. But this really solidifies our idea that taking IR finite amplitudes would solve the problem of divergences in KMOC theory or angular momentum impulse. So lots of new, like even Schwartz had a new idea for this, where he defined a new kind of Feynman rules for asymptotic regions in Feynman diagrams that we discussed. And there is also a recent paper which talks about modifying the propagator in itself, not using the Feynman propagator, but using a Coulomb propagator, which is a solution of which is not a solution of free propagating fields propagating in a free background, but when you have a particular kind of background, you would have this Coulomb propagator, and that gives you IR finite amplitude. Once you have this background and a propagator satisfying this equation would give you a IR finite Feynman amplitude.
So you don't mean box square, right? It's box.
Box.
Yeah.
Yeah. Box.
So it's like a different gauge fixing or?
Gauge fixing. No, we are here working in Lorentz gauge in this paper.
This is also Lorentz gauge.
Yes. So when you are solving this,
But it looks a little, well, it looks a little bit like giving a mass, right? The a mu term is like a mass term
mass of the field, yes.
of the field.
Yeah, of the field. Yeah.
But I don't see it exactly.
But it really came from the fact that we just converted our d news to capital D news and just
Is your phi on the left hand side or what?
Klein Gordon condition for in a background. Basically. I think that's it from my side.
No, we don't.
Yes.
Question for me.
Yes.
So you had this argument that you're fixing somehow using the fact that you have the wave functions of the particles
Mhm.
in momentum space
Yes.
to play with.
Mhm.
And you said somehow this improves things, but somehow we skipped that part. You just wrote the answer. So can you sort of give an intuition why this helps? How
Regarding
this-
something?
Right, so how you get there from fixing the wave functions?
So, okay. You have Ivan expression. So, since you're talking about Ivan here, so, this is the expression we have for Ivan. And like I said, the argument is very involved and I don't really remember it. But it's like we have these.
Mhm. Yeah.
This.
Yeah.
And they are asking us to rescale Q to Q by H in this equation.
Okay,
And similarly, all our delta functions will be also scaled.
right,
And since we have only a tree level diagram, we don't have any other thing to rescale other than the complements, which is scale like this.
okay,
And in this expression, if we do an exercise of power counting, this is h to the power 4. This is 1 over x square. This again is 1 over x square. And our amplitude in itself has 2 square here. So 1 over x square again. And then your e square is at 1 over h. So, and something like this, right? I'm missing.
yeah,
So what is Q? This Q scales as h. Sorry. So the Q scales as. Yeah. So the Q scales with this h times Q. Yeah, right. Waiting for that. And once you do this power counting. Okay, I'll do it immediately. So you have 4h for d4q. You have 1 over h square for this, 1 over h square for this. So h to the power minus 4 for this. Then you have h for scaling this q. And you have 1 over h square for scaling this q. Then you want to also scale the coupling constant, which would be 1 over h square. So effectively it is how many powers? Four.
How many do you want?
I want to say h to the power 0.
Well, so what's in the A? You have q squared in the numerator, but also upstairs you also have q squared, no? Or what's the?
Yeah, that q square will not consider in the calculation because it's higher order once we scale it.
Okay.
So we'll in the calculation we'll also only consider this.
Okay.
So that I have taken out.
Doesn't that also apply to the transfer function then?
Sorry?
Just scale it.
yeah, maybe you're scaling.
Yeah, the delta function, you have q and q square and the delta.
Yeah, but this delta function scales as 1 by x squared.
Right. Delta function squared.
Yeah, it scales the opposite to the.
Are you scaling p as well, or just?
No, understand.
Yeah, we're not talking about the inverse of delta function. We're talking about that you have a linear and cube.
Sorry, I didn't get you. What are you saying?
There's a linear term in Q, not quadratic.
The delta function, you have p1 dot q plus q
Mhm.
squared. Now those two terms scale differently.
Actually, scale is the same because p P1 plus Q whole square is M square. So, they're essentially the same. This thing.
Yeah, but now,
Well, if you just rescale Q, then the terms rescale different.
but since they are equal, so they should scale
right, but are you rescaling P or
Q.
only Q?
Yes.
So if I take this term,
Mhm.
we scale Q by H bar, then the Q squared scales by H bar squared,
Yes.
and the PQ squared scales by H bar.
Yes, yes. Yeah. Sorry.
So by the same argument, maybe you are ignoring Q squared, just looking at PQ, and then the delta functions squared by one over H bar and H.
And that would fix your problem.
I'll just
Okay.
open my thesis, maybe it's much clearer because I'm forgetting the details now. One second. Yes, I think it's that. It scales as one by H instead. It's one by H. Then you get effective power to the H power.
Right, but
Yeah.
but still somehow you got something
Yeah.
without telling me exactly
Yeah.
how you choose the phi's, the weight functions.
The phi's are not chosen in a particular form. They are just like.
But somehow you're using them. Like,
So
so
we
you
are using their arguments to look at what kind of terms we want to scale.
right, but you still get rid of the P integrations which you had before. Somehow they are not there anymore.
Yes,
They're lost.
yes, yes.
So you have to say something about what phi is to be able to do P integration.
So, yes,
So you could say it's a delta function.
it's.
I'm happy with that, but
It's probably the opposite, if it has to be localized.
It's not exactly delta.
right. But then what is the contribution from that?
Right.
I don't see.
These are all numbers somehow.
I can tell you what they say in the paper. I also don't really understand it exactly. So they say that when you have done all the scaling, your it's like. Okay. So they're saying this, all of this term, this integration over the phase space measure and everything gets in. You basically don't have to look at it. Once you're done the classical, once you're done the scaling, this picture, this thing does not account for the result. It's just this thing that we need to solve properly. I also don't understand the whole
So
argument.
you just still have it there, you're just focusing on the other part.
I think so, but I'm like I said, I'm not really sure now about how they exactly.
It's probably because it drops out when you normalize.
Yes. I think, yeah. Also, like phi's are normalized, so that.
It's more or less constant because it has to be localized in T space, momentum space, it's in position space, it should be, momentum space, it should be more or less constant.
But again, it's still not delta function properly. They have said nothing about the form of the wave function, exactly. Yeah, sorry, this exact argument given at.
Slowly varying in momentum space.
Yes, yes. To have a classical interpretation, because if the spread is too much, we can't say what the momentum exactly is. Yeah, this maybe I'll get back to you after reading the paper again, because it's a bit. I don't know, sorry. Yeah. Any other questions?
So what are the applications of this formalism?
Yes. Firstly, it makes the calculations very easy for higher orders. Secondly, you don't have to worry about the ALD radiation reaction when you're doing because classically when you're doing it at third order, you would have this radiation reaction coming in, and that you have to put in by hand. You don't have to do any of that in this kind of formalism. Also, I have seen in papers they have used this to model gravitational, the black hole binary mergers. You can get the gravitational waves through this formalism using the radiation part. Yeah. You can calculate the radiation as well, which comes from the I2 term, which is not there. But yes. Also, like, since I have done this only for electromagnetic scattering, we can also do this for gravitational scattering. Like I have done this in the thesis, and the results are right. And also, people are now using double copy to, calculate gravitational amplitudes using this formalism, rather using Yang and double copy. So yeah, that's the applications it has. There's a whole lot of work going on in word line formalism and correspondence between word line formalism and this kind of forms. Icon and all this. There's also yes. Also, it helps really in looking at the IR triangle. Not maybe the formalism as such, but the kind of work that I did, it helps you understand the IR triangle better, which is the triangle between memory effect of gravitational wave, soft theorems, and what's the third? Yeah, I I'm not sure about this third corner of the triangle, but these things were proved to be effectively the same by Strominger and his higher triangle.
Maybe water analysis.
Yes, yes, exactly. Yeah, so this work, we also got our main effects from KMOC, which I have not discussed. But yes. Other questions? Okay, listening is okay. Thanks. Thank you. I'll get back to you on this.